Alright, so this will be the video corresponding to the area and perimeter of a circle lesson. All of the worksheets and other documents for this lesson can be found on the Weebly website. For the area of a circle, we're going to use the term area, but the term perimeter isn't typically used for circles. When we're talking about the perimeter of a circle, we use the word circumference. Alright, so the do now for this lesson was to write the area and perimeter formulas for a regular, square, and triangle. This should be, basically a review, terms that you're all familiar with: square, triangle, area, and perimeter. For area of a square, we know it's length times width for any rectangle or square, and since all the sides are the same, we're going to write that as S times S, or more simply, S squared. All right, great. And for perimeter, remember we add up all the sides since they're all equal length. We can just write that as S plus S plus S plus S, or 4S. Okay, and the area formula for a triangle is base times height. So we know that area base height. And since it's a regular triangle, we know that all of the sides are the same length. And since one of the sides is labeled B, we know that the perimeter is B plus B plus B. And so we can write that as just 3B. Okay. The next part of the do now was to write in your own words the definition for the following terms. These may be terms you've seen before, they might not be. I kind of just want you all to try to get the chance to think about what those words mean. So take some time now, if you're watching the video, to think about what your definition is for those words. Okay, so for an inscribed triangle, or an inscribed shape, that is the largest shape that will fit inside of another shape. Typically, if you look at the triangle below, the inscribed triangle would be the inside one. And if we tried to make that triangle any bigger, it would be outside the edges of the circle. A circumscribed triangle is the smallest shape that will fit outside of another shape. So it's kind of the opposite of the inscribed triangle. And if you look at the shape below, the green triangle, the one on the outside of the circle, would be the circumscribed triangle, because that's the one on the outside. And if we made it any smaller, it would be inside the circle. And if you look, actually, the endpoints of the inscribed triangle, the red one, intersect the circle, and the midpoints of the sections of the circumscribed triangle intersect the circle. And that's not always going to be the case, but it will always be the case when the inscribed or circumscribed shape is a regular polygon. And what a regular polygon is a polygon with a certain amount of sides that all have the same length and angles that all have the same angle. So for the triangle, all of the inscribed, like if the inscribed polygon is a regular triangle, then all three of the sides of the inscribed triangle have the same length, in this instance 2, and all of the angles are going to be the same on that triangle. They would each be 60 degrees, because the total sum of the angles of a triangle is always going to be 180 degrees. And for the circumscribed triangle, the sides of the triangle are going to be length 4, and they're all going to be the same, and the angles are all going to be 60 also. Those are both what we call equilateral triangles, but when we get larger shapes, we call them regular rather than equilateral. The regular polygon for a 4-sided shape is something you're familiar with. We call it a square. A pentagon, a regular pentagon, would be the one that you typically use. A regular hexagon is the one that we typically refer to as a hexagon. All right, so going into this approximation of the area and circumference of a circle, we want to try to use polygons to give us an approximation. So will the inscribed triangle have a greater or less perimeter and area than the circle? So I want you to think about that and think about what your answer to that question would be, and then we're going to test it out and see if your prediction was correct. So think about that for a second. Look at the inscribed triangle, look at the area and the perimeter of that triangle, and compare it to what you think the area and the perimeter of the circle would be. And try to think about whether it would be less than or greater than. Now do the same thing with the circumscribed triangle. Do you think the area of the circumscribed triangle be greater or lesser? And what about the perimeter? And next, would using a square or a pentagon instead of a triangle give better approximations of the area and perimeter or circumference of the circle? So once you've thought about that, I want to show you all the GeoGebra, which was shown in class. We'll do area first. So if you're looking at the circumscribed and inscribed triangle, since the inscribed triangle is inside the circle, it's smaller than the actual circle. So there's empty space in the circle that the inscribed triangle doesn't cover. So the area is going to be less on the inscribed triangle than the circle. Similarly, there's area in the circumscribed triangle that isn't in the circle. So the area of the circumscribed triangle is going to be greater than the area of the circle. And so that was one of the predictions. If that's what you thought based on the picture, that's great. Over on the right, we have the area of the circumscribed and inscribed polygon and the area of the circle. And if you've seen that symbol before, that is a number. It's called pi. It's approximated by 3.14 or 22/7. And as you can see, the area of the circumscribed polygon is greater than 3.14, and the area of the inscribed polygon is less. So if we can change some things to kind of show that we can get a better approximation. So if we changed it to, let's say, a square instead, you can see that space has been cut short dramatically. And we get a much better approximation now with the square than we did with the triangle. With the inscribed square, we have an area of 2 as opposed to like 1.2. And with circumscribed polygon square, we have a 4 as opposed to 5 point something, which is a lot closer to the area of the actual area of the circle, which is around 3.1. So we just changed it from a triangle to a squares, and we immediately got a better approximation. And that's actually going to get better and better as we increase the sides. See, now we're at, with seven-sided shape septagon, we have 2.7 and 3.3. That's almost within a tenth of the actual area. And as we keep going, we're getting closer and closer to the actual circle. And at this point, it basically looks like two circles on the outside of that actual circle. And we're getting closer and closer and closer to that actual area. Once we have 30 sides on the regular polygon, we have 3.15 as the outside area and 3.1, almost 2 on the inscribed area. So that's very, very close to our actual area of 3.14. Now I want to make this a little bit bigger so you don't think it's actually just becoming a circle. When you raise the radius, you see there's still gaps between the inscribed polygon in the circle and the circumscribed polygon in the circle. And even as we increase the sides, you see those gaps getting a lot smaller, but they're still there. And you can't see them anymore, but if we make the radius even bigger, you can still see, like over on the right here, just below where it says area of a circle, you still have those gaps. So that's why we're using these to approximate but not get the actual area. Also, when you look at these radius numbers, I want you to try to notice a pattern between the radius and the area. So when we had the radius of 1, we had an actual area of the circle as pi. When we make the radius 2, I want you to just try to record the number and see if you can relate that to pi. So when we have a radius of 2, it's now 12.566. And with a radius of 3, it's now 28.2 something. So try to write those in terms of pi if you can, filling out the chart. I think it'll be helpful to look at the perimeter first when you're looking at this. So let's move over to the perimeter, and we're going to show very similar things to what we saw in the area. So for the perimeter, we see the actual circumference of the circle is 6.23, and if you notice, our pi was approximately 3.14. 6.23, and whatever the rest of it is actually double of pi. So the circumference when the radius is 1 is 2 pi. And we have our approximations at around 10 and 5. So those aren't too close, but again, if we increase the number of sides on the polygon, we get closer and closer, and we actually get a pretty good approximation as we go. So we end up with like 6.27 and 6.30 within 1 or 2 tenths of an approximation. And again, when we increase the radius, you're going to see that same gap where we're very close, but we're not exact. And the inscribed polygon has a less of a perimeter, and the circumscribed polygon has a slightly greater perimeter. Okay, so again, notice for the observation table, I want you guys to notice the circumference of the circle and try to relate it in terms of pi. So we already know when there's a radius of 1, the circumference was 2 pi. Now, if you look at the radius of 2, with a radius of 2, it's 12.56, and that looks like about double what the radius was at what the circumference was with a radius of 1. And in fact, it's actually 4 pi. And with a radius of 3, it's 18.849555, and that's actually 6 pi. So just fill out the observation chart corresponding to these values. And if we go back to the area, now we saw that like the numbers were kind of getting greater, but we could still write them in terms of pi, right? So with a radius of 1 over here, we had area of the circle is pi. With a radius of 2, it's about 12.566, and that's 4 pi. We saw that just a minute ago. And I'll give you this last one. When the radius is 3, that's 28.274. That's actually going to be 9 pi. So we can write all of these areas in terms of pi. So let's go back to our chart, and I hope you were filling it out as you were following along, but I'll fill it out here as well.